Budapest, after which he moved to Wuppertal as a postdoctoral fellow, and he worked there for a couple of years. After that, he returned to Hungary, and he was awarded the Bolyai Scholarship of the Hungarian Academy of Sciences, as well as the Bolyai Plus Scholarship of the new National Excellence Program. And we are very happy to hear about novel methods for finite density lattice QCD. Attila, please go.
Okay, thank you, Zoltán, for the kind introduction. Also, thank you everybody for logging in to my talk, and also the organizers for giving me this opportunity. So I will talk about methods, some methods at least, that have been proposed for finite density QCD, which is a notoriously difficult problem. So why is that the case? Well, lattice QCD is a set of tools to evaluate Euclidean path integrals for QCD. This means an integral over gluons and quarks, which are the fermions, psi. And then in the weights, we have the exponential of the Young-Mills section, essentially, and the Dirac action describing the fermions. Since these are Grassmann variables, we cannot put them on a computer, so we integrate them out analytically, and then we are left with this famous form of the QCD partition function, where we have this determinant, this fermion determinant, and then we would like to simulate this theory. And this is possible with important sampling methods if this determinant is real and positive, which is the case, for example, for zero or purely imaginary chemical potentials, or for isospin chemical potential, but for generic values of chemical potentials, it is not the case. Important sampling breaks down, and we say we have a complex action problem. And in such a situation, essentially, desperate times call for desperate measures. And in a way, I will review some of these desperate measures. I will talk about 3 topics. And for each, I would like to give at least some of the background, some of the basics. And also for each, I would like to give one recent example of recent work, which I participated in with several collaborators who are listed on the slide. The first topic will be novel extrapolation methods from either Taylor or imaginary chemical potential data. The second topic will be more direct reweighting methods, so phase and sign reweighting. And then in the third method, I will talk about at least some ways of dealing with sign problems, not yet in QCD, but in some toy models. So let me start with the first topic, which is working near zero chemical potentials. And the first question I ask is, what does one do when one cannot simulate a theory? And in general, what one does is to simulate another theory. So this is essentially the main idea behind reweighting, which is a very, very general idea. Given some target theory, where everywhere the T subscript means target, we have some partition function z of t, which can be written as the integral over some path integral weights w of t, which for our case are complex. We then take some other theory with subscript s, meaning simulated, with partition function z of s, which is the integral over some other weights, which are now chosen by us, performing the simulations, to be real and positive. Then one can reconstruct any expectation values, at least in principle, in the target theory, by taking 2 expectation values in the simulated theory, where in addition to the original observable, which we want to calculate, also this ratio of the path integral weights, Wt divided by Ws appears. Now this is an exact formula, but nevertheless, this is not a formula that can be numerically evaluated in most cases, and there are two reasons for that. The first one is just coming from the fact that these weights are complex, and so there can be very large cancellations both in the numerator and the denominator of this formula, which is to say that what was the complex action problem before with reweighting became a sign problem. The other problem, which is not as much discussed, but similarly important, is the overlap problem, which is that for many cases, this ratio of the weights, the probability distribution of it can have long tails, which are again not efficiently sampled with a Monte Carlo simulation. So actually in this very beginning of the talk, I was thinking that I am going to introduce the overlap problem with a very simple toy model example, which is probably everybody is familiar with, which is the Ising model. And suppose that I want to derive information in the Ising model at non-zero magnetic fields by simulating zero magnetic fields. Then in the notation of my previous slides, my target theory weights are just given by these usual two terms, so the nearest neighbor interactions and the magnetization term in the Ising model. And my simulated theory would be just the same thing at h equals 0. The ratio of the partition functions in the two theories is actually nothing else than the expectation value of this exponential observable e to the h times the total magnetization at zero magnetic field, which is nothing else than the generating function for the moments of the magnetization. And then the logarithm of this ratio is essentially proportional to the difference in the free energies between the two theories. And in general, in probability theory, the logarithm of the momentum generating function is the cumulant generating function. And this is where we see that the moments, okay, so these double brackets, I denote the cumulants here. And so this is where we see that derivatives are essentially cumulants. We also see that reweighting, at least formally, resums the Taylor expansion to all orders in the control parameter in which you do reweighting. So now let me show you what kind of things do you get. So on the left, again, keeping with this toy model example, I have the Ising model, and I compare direct simulations, which are the brown points here, with several ways of trying to guess the magnetization as a function of the magnetic field from simulations directly at zero. And the red, green, purple, and orange bands are essentially the different orders of the Taylor expansion of this quantity. One can even calculate the radius of convergence of this quantity. It is this black line. And then the blue band is just what one gets from reweighting. So there are a few things that I would like to say here. First of all, since reweighting formally resums to all orders, it doesn't really care about the radius of convergence of the Taylor expansion. On the other hand, that doesn't mean that it will be correct. So here, the statistics and the volume is chosen in a way that it actually extrapolates through the radius of convergence, but simply by decreasing the statistics, it is very easy to come up with a situation where the reweighting will fail actually before the radius of convergence. And the reason for this failure is the overlap problem. So what is on the right-hand plot are actually those histograms which one has to essentially integrate to get the ratio of the two partition functions. So it's P of M times e to the h times m for increasing values of the magnetic field. And you can see that, for example, the first one, this red 0.001, this is a nice peak, but for the larger ones, very large portions of the distribution are missing. We can only see the first part, so the two things don't have good overlap. And actually, this happens anytime you try to sample the tails of the distributions. In fact, you get a very, very similar plot if you, instead of plotting this generating function, you plot what you have to integrate for the moments themselves. So whether you do this or that at large enough orders or large enough h, you have an overlap problem. Your assumptions about statistical analysis do not hold, and reweighting breaks down, even though there is no sign problem. So then one could ask what happens in full QCD. So after this toy model example, let me show you a figure from full QCD. So the basic formula is the same. So to get an expectation value at finite mu, I can use a ratio, but now the weights are essentially this fermionic determinant at finite mu, which it turns out only depends on the ratio of the chemical potential with the temperature, which I will call mu hat throughout the talk. And now the difference is that in addition to the overlap problem, there is also a sign problem, because this thing, because of the numerator, can be an arbitrary complex number. What is shown here is a slightly weird histogram. The histogram has essentially these weights, these WT by WS, but only the real part, so that it's a one-dimensional histogram. And also it's a log-log plot. And also, because I couldn't put the negative weights on the log-log plot, I just flipped them over. So in the green curve, you have the negative weights. And in the purple one, you have the positive weights. And then strong sign problem would be visible by essentially the areas of these two curves being approximately the same. And you can see that this is clearly not the case here, especially since this is a logarithmic plot. So this is quite a large difference in the histograms themselves. What is not under control, even in this case, is actually the overlap problem. And this can be seen by this small number of outlier configurations. You can see that these are 1 or 2 hits in the entire ensemble. They are orders of magnitude larger, these weights, than the typical weights, and actually they dominate the entire average. And since these weights are not sufficiently sampled, for example, if one sees this in a simulation, then one could conclude that it's not reliable. So I think the moral is that one shouldn't be too greedy. So if one works with the simulations at mu equals 0, then one should stick to information that is reliable and that is certainly not something like a full generating function, but rather only low-order cumulants, low-order moments of the baryon number, essentially the low-order Taylor coefficients. One extra twist to this story is that one can also calculate Taylor coefficients, say in the pressure, by imaginary chemical potential simulations. This is illustrated here. So this is some observable. It doesn't matter that much for us what it is. It's roughly the baryon number divided by the chemical potential. And then it is plotted as a function of mu squared. So when this is negative, we are at imaginary chemical potential, and when it's positive, we are at a real chemical potential. And then by essentially numerical differentiation, which in this case essentially means fitting, one can estimate the Taylor coefficients of this observable. And similarly, any other formula which you could think of like a resummation of the Taylor series. So for example, here a rational function can also be estimated. What one gains with this is slightly better volume scaling. So the usually derivatives have a worse signal to noise ratio at higher orders, and with this one can work with direct calculation of lower order determinants. And the cost of this gain is essentially some novel sources of systematic errors because of this numerical differentiation. Okay, so once given something like this, so data either at imaginary chemical potential or at zero chemical potential, what can one do with it? So of course, the most naive one is just to use a Taylor expansion and see how far one can go. But increasingly, there's been interest in the community for different resummations of the Taylor series. So the most famous one of those is actually the PODE resummation, and there has been lots of activity in this. So instead of approximating functions with polynomials, here one approximates it with rational functions, so ratios of polynomials, and in some cases this is known to have much better convergence properties, and in recent years there has been lots of activity in this field. I will not talk about these papers in much detail, but such PODE approximants have been used for the phase transition line, to estimate the radius of convergence at high temperature, also the equation of state, and so on. The resummation that I will talk about more is slightly different. It comes more from a, I guess, physics motivation than a mathematical motivation. And one starts here with noticing, essentially from imaginary chemical potential simulations, that the strengths and the widths of the QCD crossover near zero chemical potentials, so at small chemical potentials, is almost constant. So here I have two plots that say almost exactly the same thing from two different papers. On the left, you have what is essentially the half widths of the transition. You can see that it's, I don't know, it's like a 15 MeV at mu equals 0. The transition temperature is around 158 MeV or so. So it's a pretty wide crossover, which is known. And then one can extrapolate this width parameter using imaginary chemical potential simulations to real chemical potentials. And what sees is that it starts with a slope that is 0 within errors. The errors are tiny. And as far as we can tell, it always stays constant. On the right-hand side, there is a different manifestation of a similar thing. This is the baryon number divided by the baryon chemical potential. And it is plotted as a function of the temperature times. And then here I have 1 plus some constant times the chemical potential squared. And in the different colors, I have simulation data points from many different imaginary chemical potentials. Now these, as you can see, when plotted with respect to this variable, are almost exactly on the same curve, especially in the crossover region. So this seems to be an empirical observation about lattice QCD at small density. Just a comment that this is not entirely unexpected. So the cause probably has to do with the two-flavor chiral limit. So here is a toy model example. Similarly to my Ising model, toy model example, this is also something that anybody can do in an afternoon. So you take a two-flavor quark meson model, and then just solve it in mean field and plot some measures of the strengths of the crossover transition. I showed you two such curves. So one of them is the sigma curvature mass squared, and the other one is the inverse of the temperature derivative of the sigma field. And you can see that both of these are very much constant. Both of these, like width parameters for the transition, are very much constant at small chemical potential, and this is essentially due to the fact that in the two-flavor chiral limit, these models have a line of second-order transitions. It's essentially due to the fact that at small chemical potential, what governs the strength of the crossover is the quark mass, and you cannot make it really stronger by introducing a small nu. Okay. So I think this is probably the case, and also there's some lattice evidence that also in QCD the two-flavor crossover might be second order. So I think this is the cause, but whatever is the cause, it's an empirical fact that there is some approximate scaling variable, and actually one can use it to construct extrapolation schemes. And this is my one slide on our extrapolation scheme from last year, where we introduced essentially an ansatz. We take some observable, which I just call F. It could be, for example, the baryon number divided by mu b. And then we say that this observable at some temperature T and some chemical potential mu b hat is the same observable F at some other temperature and zero chemical potential, and it is this Tf prime that we tailor, essentially the Tf prime divided by T that we tailor expand in the chemical potential. This is a resummation, because even if I truncate this at the very first term here, it will generate an infinite number of terms in the ordinary Taylor expansion. It is also expected to converge fast if you have such an approximate scaling variable, because the kappa 2 in that case is actually weakly temperature dependent, and the kappa 4 is small. And the paper that I would like to talk a little bit more about is our paper from last month, where we extend this scheme from zero strangeness chemical potential to non-zero strangeness chemical potential on the strangeness neutral line, which is the most important for heavy ion phenomenology. And actually, we could use almost exactly the same procedure, but we do introduce one slight improvement at high temperatures, and that is what I first like to talk about. So a problem with the original scheme, if you go back to this definition here, was that if this left-hand side is larger than the Stefan-Boltzmann limit of the right-hand side, that is the infinite temperature limit of this, then this equation cannot hold. And that puts a limitation, especially at high temperatures, on how far such an extrapolation can work. Very simple trick to remove this problem is to slightly modify the scheme and divide both the left and the right-hand side by its own infinite temperature limit, which is now chemical potential dependent in general, or at least mu b by T dependent in general. And then on the left, you can see the type of curves that you get. So this is the baryon number divided by its own Stefan-Boltzmann limit for zero chemical potential in black, in green, and in red, two different imaginary chemical potentials. What this correction does is that all of these curves tend to 1 at infinite temperature, and therefore also this first correction coefficient and also all of the rest will go to 0 at high temperatures. So what this correction does is that this fast convergence at low orders, which was mostly in the transition region before, now also is extended to high temperatures. And this can be seen in the right, where actually these two schemes, so the scheme from last year, which didn't include this extra factor, this is the first coefficient there, and you can see that at large temperature it blows up, while with this infinite temperature correction it goes to 0, and we have a fast convergence at low orders. So we use this to calculate the equation of state, both at the strangeness neutrality. So here I have the pressure as a function of temperature for different values of mu baryon by T, which are the different colors. And we also used it to calculate the equation of state beyond the strangeness neutral line, which might be useful if you want to have to know about local imbalance of strangeness, because, for example, in a heavy ion collision, only the global ERD spin is conserved. And what is shown here for different values of the chemical potentials in different colors are actually the first correction coefficient along the strangeness neutral line of the pressure in this ratio of the strangeness with respect to the baryon number. So you can use this to extrapolate the pressure to non-zero strangeness expectation value near the strangeness neutral line. Okay. So with this, I summarize the first part of my talk. In the very beginning, I essentially emphasized that one shouldn't be too greedy. So when one has simulations at 0 or imaginary chemical potentials, one should stick to low order cumulants. And if one wants to have faster convergence or possibly to go outside the radius of convergence, then one can resum those coefficients. And what I talked about in detail is this kind of joint expansion in the temperature and mu, which exploits both the existence of an approximate scaling variable and also is modified to have also fast convergence at high temperature, which we use for the equation of state. Now, one comment is that I don't ultimately know the convergence properties of this scheme. I know that it is not a Taylor expansion for the pressure, so the region of convergence is not a circle in general, but its shape, I have no idea. Okay, so ultimately, when we do this, we are still doing analytic continuation, which is known to be ill-posed. So in my opinion, what will come out of this is probably more and more accurate equations of state in the crossover region, but if one wants to go to really high densities, then one has to try new methods. And my second topic is an attempt along this direction. It's about more direct reweighting methods. It's essentially these two papers, but mostly the second. So if you remember from the beginning of the talk, when one tried to reweight from 0 chemical potential, the main bottleneck was the overlap problem. In these weights of the target divided by the simulated path integral weights of the partition function. If this could be avoided, so the question is, are there reweighting schemes where somehow the simulated weights are chosen in a clever way such that this ratio cannot have long tails and therefore cannot have an overlap problem. And one obvious way to do this is to make sure that these weights they take values from some compact space, like a finite interval, for example. And in that case, by construction, they can have no long tails, and one can calculate the ratio of the partition functions or the pressure difference between the target and simulated theory without encountering heavy tail distribution, so any overlap problem. And then one could have a scheme for the equation of state that does not have an overlap problem. And there's two relatively simple ways to achieve this. The first is the more famous. It's phase reweighting. The target weights are still the same, but the simulated weights are now the weights with the absolute value of the determinant. Here, the severity of the sign problem is measured by the expectation value of these phases of the determinant in this so-called phase quenched ensemble. Another one, which could also work, is sign reweighting. Here one changes both the target and the simulated ensemble. So the simulated ensemble, you take the real part of the determinants. The target ensemble, you take the real part of the determinants, and in the simulated one, you take the absolute value of the real part of the determinant. And what you achieve by this is that these reweighting factors, these ratios, are pure signs. It's a one-parameter Bernoulli distribution. And in this case, the severity of the sign problem is measured by these expectation values of these signs. Now, one has to be a little careful with this, because this substitution of the determinant with its real part can be done in the partition function, but in generic expectation values, it can't, because the path integral representation just has the det and not the real part of the det. But since it can be done in the partition function itself, it can also be done in anything that can be written as a real derivative of the partition function with respect to chemical potentials, quark masses, gauge couplings, and so on. And fortunately, that is enough for bulk thermodynamics. One more thing to note is that actually the first appearance of this scheme is in this paper a very long time ago in a Lattice conference proceedings, where they note that out of reweighting schemes where these reweighting factors are only some function of the phases of the determinant, this is the optimal choice with the weakest sign problem. But then they immediately note also that it's pretty hard to come up with an efficient algorithm for this, so they never simulated it. And this is one of the things that we did recently. But before discussing that, let me talk 2 minutes about the first one, the phase quenched ensemble. So the phase quenched ensemble is equivalent for two flavors, two degenerate flavors with the same mass. It's equivalent to an isospin chemical potential. Now, at the finite isospin chemical potential, this SU2V symmetry for vector symmetry for two flavors is explicitly broken by the chemical potential to a U1. And then inside the pion condensation phase, this U1 is further spontaneously broken by a pion condensate. That means several things. One of them is that actually this phase quenched ensemble, as it's written here, is very difficult to simulate. Essentially for the same reason why zero quark mass is very difficult to simulate, because there's a Goldstone mode, and that breaks standard hybrid Monte Carlo algorithms. Also, an expectation, mostly coming from model studies, is that the sign problem inside this pion condensation phase, when one does reweighting, is severe. So the first thing, I guess the first technical achievement of these papers that I'm talking about is that we actually managed to simulate both the phase-quenched ensemble with no explicit breaking term, so in the symmetric limit, as well as the sign-quenched ensemble. And then the first thing we measured is actually the severity of the sign problem. So this is for the sign-quenched ensemble, which is blue and black, and for the phase-quenched ensemble, which is orange. This is the severity of the sign problem. It is 1 when there is no sign problem, and it is 0 when there's a very severe sign problem. On the left, you can see it from at a fixed temperature as a function of the chemical potential. And on the right, you can see it as a function of the temperature for fixed values of the chemical potential. And a nice feature of this is that these curves here that you see, they are not fits. Actually, they are predictions of a very simple model for the severity of the sign problem. And this very simple model for the severity of the sign problem only uses data, QCD input from 0 chemical potential, where one has to measure a particular light quark susceptibility. And knowing this, we can give a very accurate prediction on how severe the sign problem will be, which allows us to have a pretty good idea of how far we can go, for example, in chemical potential and in volume. And at least on this volume, what you can see is that the sign problem remains manageable, essentially in the entire beam energy scan range. The first plot for this, for the physics results, is actually something that I talked about in the first section of the talk, which is this approximate scaling. Here I show it for the renormalized chiral condensate as a function of the temperature. So here in the middle, in orange, I have this renormalized chiral condensate as at a 0 chemical potential. On the right, in blue, I have it at an imaginary chemical potential. And on the left, in black, I have it at a real chemical potential. And then when I plot the same thing as a function of a similar scaling variable, so t times 1 plus some constant times mu baryon divided by t squared, the curves again approximately fall on the same curve. So this collapse works directly at real chemical potentials as well. What we saw in the imaginary direction is also confirmed directly at a real chemical potential. Another example that I would like to show you is at a fixed temperature, which here is 140 MeV, and several chemical potentials, so up to 480 MeV. And it's again the renormalized chiral condensate, and it's again, like in some of the plots before, plotted as a function of mu b squared. So the blue points are actually points from imaginary chemical potential simulations, and the black points are direct points at a real chemical potential from sign reweighting. They are also compared to what one would get from an extrapolation from these imaginary chemical potential data. And while they do agree, the error bars on the direct points are actually remain small up to relatively high chemical potentials when for example, the two ansatz that I use here for the extrapolation start to differ. So how would I summarize that? At least on these volumes, the direct method penetrates the region where errors from the analytical continuation already start to blow up. So what was achieved here is is simulations of the phase and the sign quenched ensembles without this explicit breaking term. It's also direct in the sense that one has no analytic continuation problem, and it is guaranteed by construction that at least in the pressure difference between the target, so essentially in the pressure, there is no overlap problem. What is not guaranteed is in that other observables, there is no overlap problem. That might be the case, and that I'm studying right now. Also is practical that we can guess very effectively the severity of the sign problem from simple zero chemical potential simulations, which means the method is also kind of practical right now. And everything I showed you was with n tau equals 6, so 6 time slices with the decent discretization, so 2 stout improved fermions. And right now we are running n tau 8, and at these moderate volumes, so roughly 4 Fermi, say, there is no real problem in covering the RHIC beam energy scan range. Okay, but look, this is still a brute force method in a way, because one has to overcome the sign problem, essentially by statistics. So obviously, eventually, one has to do something with the sign problem itself. And this is not yet possible in full QCD, but just to try to give you some indication of what might be the future, I will cover briefly one set of methods which try to deal with the sign problem, and those have to do with complexification of the fields in the path integral. There's essentially 2 ways one could go. So you have some oscillating integral in n real variables, and then there's essentially 2 directions. One could either enlarge. So by complexification, one could mean enlarging the space to the double that size, so n complex variables instead, in which case one works in a space that's double the dimensions of the original, which is this is what complex Langevin does. Or one could deform the original integration manifold, which was some manifold here. One could keep it to be the same dimension, but deform it to be some submanifold of this double-sized one. And these are methods based on contour deformations. And essentially, there's 2 subclasses of this. You have either methods that are based on Lefschetz timbals, or you have methods that are based on path optimization, which is the only class of methods that I will talk about in detail. So for complex Langevin, I have one single slide, which is the main status, essentially since a long time. So there are, this type of approach has correctness criteria, which is known since 2010, so quite a long time ago, which are sufficient, but not necessary. Necessary conditions are not known. The sufficient conditions are holomorphicity of the full action, which for QCD is the gauge action minus the logarithm of this fermion determinant. And one can immediately see that this already fails for full QCD because the determinant has zeros. And then this has logarithmic branch cuts, so it's not holomorphic. The second one is that distributions of physical quantities, like the gauge action or the Polyakov loop, for example, should decay fast enough in the complexified directions. And these 2 problems lead to what is essentially the status quo, is that at the moment, complex Langevin cannot do small temperatures, so say below the transition temperature, and it cannot do small quark masses, meaning physical quark masses. To have some idea of what is being done, I here have some recent papers that one could look at. One direction of research is to check a posteriori by several by essentially checking whether the simulation satisfies these criteria or not, whether the systematic error coming from the complex Langevin is safely smaller than the statistical one. Another direction is just exploring QCD at large quark masses and large temperatures. And the main challenge remains to extend the method, the region of applicability of a method in a reliable, provable manner. Okay. So now, what about the other class of methods, contour deformations? So again, we start with some theory with complex weights, complex action. And then we define the corresponding phase quenched, where you just take the absolute value of these weights, and sign quenched, when you just take the real part of the absolute value of these weights theories. And then if these integral weights, e to the minus f, are holomorphic functions of the fields, then such a thing can be interpreted as a multidimensional contour integral, and with some contour deformations, one can show that the partition function remains the same. However, even if the full partition function remains the same, the integrons for the phase quenched or sign quenched ensembles are not holomorphic. So the ratios that measure the severity of the sign problem, like the expectation value of the phases in the phase quenched theory or the expectation values of the signs in the sign quenched theory, are not invariant under such contour deformations. So it is then possible that there exist contours where these ratios are much closer to 1 than on the original ones. And the goal is to somehow find such integration contours. A big plus for this method is that the action itself does not have to be holomorphic. Only the path integral weights have to be holomorphic, so e to the minus s. And that means that at least for correctness, the fermion determinant is not a problem, unlike with complex Langevin. What could still happen is that depending on how dense are the zeros of the determinant, the kind of improvements one could achieve are different. But at least for correctness, there is no fundamental obstacle, not even in full QCD. But the disadvantage is that from the start, we essentially gave up on solving the sign problem and only tried to make it milder. The historically first example of these methods were the Lefschetz timbals, which were proposed in 2012 by Cristoforetti, Di Renzo, and Scorzato. Here, essentially, the criteria that gives the new contours is that the imaginary part of the action should be constant along these contours. And the main difficulty of the method is that in order for the partition function to be still the same, then the contours in general split into several disconnected ones, which are called the timbals. And first of all, it is very hard to find all of the timbals that contribute to the path integral. The timbals have relative phases between each other. So on each timbal, the phase of the imaginary part of the action is constant. So you have no phase fluctuations from this, but it's a different constant on different timbals. So we say it has a global sign problem, and also because the timbals are curved. You have a Jacobian, which is in general complex, and that is usually called the residual sign problem. But it's actually not these two sign problems that remain the most challenging, but actually the first thing, just finding all of the timbals that contribute. And for this reason, most of the recent activity in the field actually focuses on approaches that relaxes this requirement of finding all the timbals and only works near timbals or in this very recent example, for example, there is a method in which the authors patch points in parameter space where they can show that a single timbal is enough, and then they perform Taylor expansions around these points, not just the original contour at mu equals 0. Okay. What about this other class of methods, manifold optimization? This is a simple idea. So you consider some family of integration manifolds, which are parameterized by some number of real parameters. And then you just simply measure these, the severity of the sign problem, and then try to optimize these parameters such that the sign problem is weak. This method was proposed actually 5 years ago, and since then it was applied to several models of different complexity, mostly in 1 and 2 dimensions. One interesting example is 2+1, the Turing model, where an extremely simple ansatz, where you just shift essentially by a constant imaginary part all of the fields, leads to a very drastic improvement in the sign problem. So my last few minutes, I would like to show you one case study of such a contour deformation in a model, in a toy model, which needs a slightly more complicated ansatz, but is still very tractable, still very simple. So this is the XY model at finite chemical potential in 2+1 dimensions. So it's a scalar field theory where the scalar fields are, well, XY model, so they are constrained to be a unit vector essentially. So they are parameterized by an angle, and the complex action in these 2+1 dimensions contains the cosine of the difference between the neighboring angles. And if the neighbors are in the time direction, then you have an I times mu here. But this is extremely far from QCD, but at least there are some similarities. Like, for example, the integration variables are compact, like with QCD, where SU3 is a compact gauge group. It has a Roberts-Weiss periodicity at imaginary chemical potential. Also, like with QCD, the complex Langevin approach fails for small values of this coupling beta, already at 0 chemical potential, which is again the same as in QCD, and also the chemical potential is introduced similarly in this non-linear manner, like in Lattice QCD. On the other hand, unlike QCD, there is a known formulation without a sign problem, and that can be compared to different approaches. So what kind of contour deformations are allowed in this model that leave the partition function invariant? So this is illustrated on this figure. So essentially, the original contour goes on the real line from -pi to pi. The integrand is both holomorphic and also periodic with period 2 pi. That means that I can always close a contour like this between the original contour and some new contour. So say going the original, going up, then connecting the 2 green points and going down. And then the 2 vertical pieces will cancel because of this 2 pi periodicity, and because of the Cauchy theorem, the entire thing will be 0. So essentially, as long as one has the same imaginary part at real part -pi and +pi, the integral remains the same. And this remains true also for multi-dimensions. So if I fix all of the other fields and then as a function of the one free field, this remains true, then all of those contours are allowed. And since we are essentially parameterizing periodic functions here, it's natural to use Fourier series. And we tried several different ansatzes. I only show you one. I show you one which has a very small number of parameters, which are very cheap to optimize, and it leads to a very good improvement in the sign problem. Until you have just 2 free parameters. So the deformed field at some point x depends on points depends on the real part of that same point, and also on the temporal neighbor. So that x plus 0 means the temporal neighbor. And then I just have the real part is what it is, and then the imaginary part is just a low-order Fourier series in the angle difference between the temporal neighbors, 2 parameters. And if one optimizes these 2 parameters, then this is the kind of improvement that one can achieve. So please ignore the green curve. That's a different ansatz. I only told you about the blue ansatz. And this is at a fixed volume, fixed temperature, and as a function of the chemical potential, what is the severity of the sign problem, and it is on a logarithmic plot. Here in this region, there's like a factor of 100 difference in this, which in statistics means like a factor of 10 to the 4 on the optimized contours. The sign problem is still exponential, but it is exponentially reduced in the sense that the exponent is greatly reduced, and so much larger chemical potentials can be simulated. Here is a very similar plot, but now at a fixed chemical potential and as a function of the volume. Again, the blue is the optimized contour, which is a line here on the logarithmic plot. So it's still an exponential function, but the exponent is again greatly reduced compared to the original contours. So essentially, what can be achieved is with a very simple polynomial time optimization, one can have an exponential increase in the statistics. Okay. So obviously, this is not QCD yet, and there's many technical challenges, but this is a direction for the future. Here, I just show you physics results, which is just the expectation value of the action at a fixed volume as a function of the chemical potential squared. And here you have the unoptimized contours, and you can see that the error bars blow up at a pretty low chemical potential. And you have the optimized contours here in blue, which are actually compared to the sign problem free formulation in this model. And while they do give larger errors, you can see that you can go pretty far in the chemical potential. In fact, here, there is actually a phase transition in this model. You can see like a slight change in the slope here. With detailed analysis, you can see that this is a phase transition. So you can even go through the phase transition with reweighting in this model that way. Okay, so I said that I will talk about new methods for finite density lattice QCD, but the fact of the matter is most of the things that are on the market are actually variations on old methods, but that they are still useful. I talked about resummations of the Taylor series, and it's in particular a joint expansion in the temperature and mu, which allows one to exploit the existence of an approximate scaling variable, and it also allows one to exploit the known infinite temperature limit of thermodynamic observables in the extrapolation, and that way one can achieve pretty fast convergence at low orders. I also talked about more direct reweighting methods with the motivation of not having an analytic continuation problem anymore, and here the main achievement is finally simulations in the phase and sign quenched ensembles, as well as which allow for results on the equation of states A without the overlap problem. And in the end of the talk, I talked a little bit about what I think could be the future, which may be these complexification methods. Truth be told, they are far from working in full QCD. There's many technical challenges there, but some of those technical challenges are actually the same technical challenges that are there already with the more direct reweighting methods. So just one example, how to calculate effectively the residual phase that you have to use for a reweighting. Just another example, if you want this to ever work with full QCD, you need to start your optimization somewhere. So you need to be able to do, again, for example, phase quenched or psi-quenched simulations effectively. And I really hope that in some years, I don't know how much, these two directions can join. So thank you all for listening. And
thank you very much, Attila, for this really nice talk and excellent results. I'm looking for questions. There is no question in the chat window, but I see hands. So Claudia, go on.
Yes. Hi, Attila. Thanks for this nice talk. I had two questions. One on the first part where you show the comparison, the toy model with the Ising model. I was wondering, so you show a radius of convergence there, and sometimes in QCD you wonder how to identify the actual radius of convergence in case there is a critical point. So here you have a Taylor, and then you have this location of the radius of convergence, which you know where it is from the critical point of the Ising model. So I was wondering, from the Taylor expansion, what can you actually reconstruct this location? Can you tell anything?
Yes, so actually this line was reconstructed from the Taylor expansion. But again, this is the Ising model, so it's very cheap. I have much higher order cumulants than what is available in QCD. But how to do it if you have good enough data is essentially more or less known. So there are several ways. But this line is actually estimated from the data. So I have yes.
Okay, but how many?
This is actually not from the universal expectation, it's from the data itself.
How many coefficients did you need to see a convergence for the radius location?
Okay, so so around 12, 14, something like that.
Okay. Okay, so if you would look only at the first 2 or 3, like we have available from real QCD.
I mean, the first 2 or 3 are okay. So the first 2 or 3 are not that bad already. So the first 2 or 3 are like, because here I actually chose on purpose a point that is very close to TC. So it's slightly above TC. The radius of convergence is very small. And actually for this particular data set already, the first few coefficients gives it to you in like, I don't know, 30% or something of that accuracy. So it's not that bad, actually.
Okay, so the second question I had was about the second part where you show these very exciting results at finite real chemical potential. I was wondering how, in terms of resources, so you showed the results for this small volume with tau equals 6. So how does it scale? How long did it take to generate those? And if you want to go to tau 8 or 10 or so, how does it scale with that?
Well, so with the volume, it scales exponentially. With the lattice spacing, it doesn't. So n tau 8 is only polynomially more expensive than n tau 6. But say aspect ratio 5 is exponentially more expensive than aspect ratio 3. So as it is, I think aspect ratio 3 is roughly what can be done with the type of resources that are realistic with I don't know, with like a standard computer time project.
But even if you say it is polynomial, it's a high power of the polynomial.
Yes, it is a high power of the
Is it
polynomial.
9 or is it 9 or how much? How much is that?
So the bulk of the cost is the calculation of the residual phase. And the residual phase is so this essentially goes with dense linear algebra. So you have to calculate the eigenvalues of a matrix that goes like volume by volume.
Volume
That's
3.
so it's essentially volume to 3 or linear size to the 9.
Yeah, and that means that you have a 9th power in the.
So in NS you have the 9th, or sorry, in NT you have a 9th power. Yes.
Yeah. So it's a polynomial, but still a very small.
Polynomial, but a high order polynomial. Yes.
Any further questions? Either in the chat or I see Nushu raised his hand. Hi, Nushu.
Yeah, hi, Zoltan. Hi, Attila. Thank you for the nice talk. I'm not an expert on this. Your talk looks very nice. I take Zoltan's word, excellent result. But I do have a question. I think on the next slide, I have two questions on this slide.
Okay.
Now, I do not understand or follow the argument. Why in the imaginary part, the theory converges so well, and on the real part is diverges? This is one question. Oh, second one is, what do we learn? If this is the case, is this physics issue? Is it mathematics issue? If this is the case, what do we learn by studying imaginary part? Why not just mirror that? In 23 page, previous page, you can see very nicely symmetric between imaginary part and a real part. You get my question. So.
Okay, so I try to answer. I'm not 100% sure. So in the imaginary direction, there is no sign problem. In the real one, there is. Of course, eventually the two will be very different. So we know that the structure of the theory is very different in the two directions. So eventually the two should be quite different, and this shouldn't be symmetric at all.
Is this physics? Is it mathematics?
Well, I mean, it's...
Is there physics behind this?
Well, there is. I mean, it's very different, the two directions. So in the imaginary direction, there's periodicity. In the real direction, there isn't. In the imaginary direction, high order baryon, so very high baryon numbers always give a very small contribution to the ground canonical partition function. In the real direction, that is again not true. So there's many differences between the two. If it looks symmetric, that means that we are in like by eye, then that means that we are at a small chemical potential for the moment.
Then what do we learn by studying?
Then we still learn what happens at small chemical potential, certainly. And the point is to eventually go further.
Okay. Okay.
Then just the
bottom line is, from your calculation, where should we stop using these predictions on the real part? Where do you feel comfortable? It's safe, mu b over t.
You mean the extrapolation?
Yeah.
Well, that's very difficult to tell because it's an analytic continuation. That's why I'm working on the direct results. Here, it turns out that the extrapolation is okay because the direct result tells you the same, but it's very non-trivial. If you don't have the black points, it would be very non-trivial how far you can trust this orange bar, for example. That's, I guess, the main motivation for this second part of the talk.
Well, perhaps the question is, the divergence is arbitrary, or do we have any control?
So what do you mean by divergence?
I mean, sorry?
What do you mean by divergence?
Sorry, that becomes the uncertainty becomes, the band becomes wider and wider when we go to higher.
But that's because you're doing, because these come from the blue points only. And if you do an extrapolation, then the farther you extrapolate, the more uncertainty you have. So that always looks like this.
So let me rephrase the question of Nushu. In principle, you can use in the analytic continuation, aka polynomial fit, also your black points, the direct simulation points at
exactly, and then
that
this
means you can go far further away.
Exactly. So in principle, you could put the black points also in the extrapolation, and then your error, your enlargement of the error would start here and not here.
Yeah. And how far you can go when, let's say, these two expansions, polynomial and fugacity, will start to deviate from each other, which would be a sign for your for losing control over the analytic continuation.
You mean if I put in all of the points?
Yes. That's somehow Nushu is asking. I mean, wants to know what is the highest real mu value you can push if you have everything in your method.
Okay, so for that, I would actually say to wait until we do this for N08, because at the end of this range, where you could extrapolate, actually the chemical potential in lattice spacing units is already relatively large. So in principle, you could go to like mu baryon by T equals 4 or something like that, but I would be a little worried then that it's only N tau 6.
Okay. So that's a clear answer. It has still a relatively large cutoff effects, but in principle, it is possible to go mu over T up to 4. That's what the answer.
For example, yes.
Yeah. Does it answer your question? No?
Sort of.
More or less.
I have to think more. Thank you very much. Yeah.
Okay. Then I see the hand of Akira Onishi. Go on, Akira.
Yeah, thank you very much for your nice talk. And I have a question about your third part on the XY model. And if I understand correctly, then your imaginary part is just a function of the real part on the same point. Is it correct?
Of the same and the neighboring points.
Oh, neighboring point. Okay, then this kind of how to say, nearest neighbor point variable.
So actually,
imaginary part as a function of the imaginary that point, and the nearest neighbor point is working well in other models. Such as the 5/4 or some other models, or is it just this model?
Okay, so what works will certainly be model dependent. So even in this model, we tried ansatses that are different from this. So we tried going to further neighbors, for example. And we tried going also not only temporal neighbors, but also spatial neighbors. And in this model, out of the small parameter ansatz, this was the best.
Oh. Okay, and you mean that we have to try and error for some examples, and is there any systematic way to do it? And do you know some systematic way?
Well, the systematic way would be to try to approximate actually the timbres with such an ansatz. That is in some sense also possible. So that would be a more systematic way, but it's actually not guaranteed that that is the weakest sign. That is the weakest sign problem one can get. For example, because of the Jacobian, the timbres completely ignore the Jacobian. on the thimble, for example. When you construct them, if you do this optimization, you also optimize for the sign problem coming from the Jacobian. So I'm not 100% sure that the best way is to approximate the thimbles with the ansatz, but it is technically possible to do it. To approximate thimbles with some ansatz.
Symbols or the symbol motivated tangential space or something like that. Okay, that may be a good starting point. Thank you very much.
Thank you. I do not see any hand, and I don't see any question in the chat window. So perhaps then I ask something on page 34.
Okay.
You see that your optimized technique is going to be very difficult on the 16 to the 2 lattice.
Yes.
Which is 256 lattice.
There's also a third, so n tau is always 8 here, so it's 16 squared times 8 is what it means.
I see. But it's already untracked.
But it's already difficult, yes. Yes.
Yeah. So this is just a dozen or so lattice points in QCD if you just look at the number of degrees of freedom. Your thoughts on that?
Okay, so if okay, so my first thought is that even in QCD, we are already doing something that is kind of brute force already. And if I could achieve even like a factor of 10 in the statistics, I would already be very satisfied with that. So the first thing why this contour deformation, I think, has a chance of working even in the short term is because kind of your goals are more modest. You don't want to solve fully the sign problem, only reduce it. And since in QCD anything we do is somewhat brute force anyway, even a factor of 10 in statistics would be huge. And here, this is what? This is a factor of 10 to the 3 in the statistics or something, 10 to the, and probably it's something like 10 to the 3 in the statistics. So it's quite substantial already. Does that answer your question?
Well, I was much more thinking about the number of degrees of freedom. So you're right, it is an improvement on this expectation value of the sign, but still the number of degrees of freedom is very, very little. And we have seen many ways to solve the sign problem for small systems. So it's always easier to solve it for small system. As you said, it is exponentially getting worse. But you say, don't worry about that, even if you can.
No, I'm saying I worry about it a lot, but what I'm saying is that even in small systems, actually, for QCD, say with physical quark masses, there is nothing even close to this.
To this improvement.
So even on small lattices, for example, complex Langevin doesn't work for QCD at low temperatures and small quark masses. And you have to start somewhere. Okay.
Absolutely. And as you
I don't think it's realistic to think that in a year the sign problem will be solved.
Even for realistic QCD systems, yes. So don't be greedy. That was your message.
Yes, my comment is don't be greedy. Yeah, I guess that's a good way to put it. Yes.
That's the bottom line.
We're not trying to be greedy. We just need an answer.
Absolutely.
Right. Our data reach the B- scan reach the mu B over T approximately 3. And my question on page 23 again is, this calculation will not be affected by potentially critical point?
It is affected by it. So this
I thought this is affected by smooth crossover so far. Nothing to do with critical point yet. Is that right?
Okay, so it is one volume. So you cannot in a fully controlled manner discover a critical point with one volume, but you can still have signals for it. And actually,
okay.
So for example, a signal would be if this type of collapse curve starts working less and less as you go to higher chemical potentials, that would be a signal for criticality. You wouldn't be able to tell where the critical point is with absolute precision from that, but it would be some signal. And then that would already be something. So actually, this is something that we are trying. So to have a full 2-dimensional scan, both in temperature and chemical potential, roughly in the RHIC range at a finite volume. And then look at these collapse curves, for example. This is something that we are working on.
Good. I do not see any further question. I do not see any further hands. So we thank again Attila for this very nice talk and the excellent discussion afterwards. And I wish you all the best, and stay healthy, and see you next time. Bye-bye.
Thank you all.
Bye-bye.
Bye.
Bye.
Goodbye.
Bye.